Given f at x is equals to that 8.1, determine the coordinates of the turning points of f. So f at x is equals to in order to find the coordinates of the turning point, we need to find the derivative of f at x. The gradient at the turning point is equals to 0. I'm just going to divide by -3. So here I'll be left with x squared minus 4x plus 3 is equals to 0. And the factors of 3 is just 3 and 1. Since this is positive and that is negative, both of these are going to be negative, so that when I say -1 times -3, I get a positive 3. X should be equals to 1, or x should be equals to 3. Now I'm going to substitute into the Muller function. This is going to be equals to 0 because I have a repeated root at x minus 1 squared. If you have a repeated root like that, it means that that is going to be the turning point as well as the x-intercept. Here I'm getting a 4. Therefore, the coordinate of the turning point is 1 is to 0, and the other one is 3 is to 4. Draw the sketch graph of f. Clearly label all the intercepts with the axis and any turning points. So we need to find the coordinates of the x-intercept and the coordinates of the y-intercept. So I'm given that as for x-intercept, set y equals to 0. So x minus 1 squared should be equals to 0, or negative x plus 4 should be equals to 0. So the coordinates of the x-intercept will be 1 is to 0, and the other one will be 4 is to 0. For y-intercept, set x equals to 0. So that's going to be a 4. So I have 1 is to 0, and the other one is at 4 is to 0. And there I have a 4. The other coordinate is 3 is to 4. The other turning point is at 3 is to 4. So that's my sketch. Use the graph to determine the values of k for which negative x cubed plus 6x squared minus 9x plus 4 is equals to k. So all of this is equals to f at x. So f at x should be equals to k. We'll have 3 real and unequal roots. Okay, so I have 2 equations. One is y is equals to k, and the other one is y is equals to f at x. So for these type of questions where they want you to find for which values of k, we use the coordinates of the turning point. So that is 1 is to 0, and the other one is 3 is to 4. We use the y value of the turning points. And then you draw a horizontal line like that. So y is equals to, at this point, it lies on the line y is equals to 4. And the other one is on the line y is equals to 0. Okay, so k should lie anywhere in between here. So k can be anywhere. Okay, so in other words, k should lie between 0 and 4. The line g at x is a tangent to f at the point of inflection of f. Determine the equation of g. So f at x is equals to negative x cubed plus 6x squared minus 9x plus 4. So in order to find the point of inflection, we need to find the second derivative of f at x. So this is the first derivative. And then we are going to equate it to 0. And then we substitute that x value into the mother function. So I'm getting a 2. This means that the coordinates of the point of inflection is 2 is to 2. Now we know that g of x is given by ax plus b, where a is the gradient. We currently don't know what the gradient is at the point of inflection, but we can find it because we know that at the point of inflection x should be equals to 2. So I need to find the gradient when x is equals to 2. So I'm getting a3. So y should g of x should be equals to 3x plus b. I'm going to substitute that 2 is to 2, the point of inflection. Therefore, g of x should be given by 3x minus 4. 8.5. Calculate the value of theta, the acute angle formed between G and the x-axis in the first quadrant. So tan of theta should just be equals to the gradient of G. So theta should be equals to arctan of 3, which is 71.57 degrees.